Okay, so we've got a complex number z, and we know that it satisfies this condition. So when it says sketch the locus of these points, we basically want to sketch a diagram that shows where z could be on the Argand diagram. So we're going to think about two different ways of doing this. The first way is geometrically. So we're always going to do the same thing when we do it geometrically. We want to get what's inside the modulus symbol as z minus some complex number. And the reason why we're doing that is because we know if we've got z minus a complex number, then if we take the modulus of that subtraction, it's going to be the distance between z and whatever point this is here. So inside the bracket, we're going to have to put 5 plus 3i, so that when we expand the bracket, we're going to get z minus 5 minus 3i. So we can think about this geometrically as the distance between the complex number z and 5 plus 3i is equal to 3. And remember, that's because if we do z minus this point here, it's the vector that takes us from 5 plus 3i to z, and we want that length of that vector to be 3. So if we think about that in the Argand diagram, let's sketch this point 5 plus 3i over here, and we want to sketch on the locus of points that are a distance of 3 away from this point. So it's going to touch the real axis, and it's going to have a radius of 3. It's going to be a circle. Now notice that I've shown that it touches the real axis. That's really important. If it didn't touch the real axis or went over the real axis, then the examiner wouldn't be convinced that you know that this has radius 3. But this shows that really clearly that it has radius 3. Let's just check that that works. So we've got this point 5 plus 3i, and let's choose any point on this circle. Let's say this point here, which is what we could say is z. Z could be anywhere around the outside of the circle. This vector here, z minus 5 plus 3i, is the vector that takes us from 5 plus 3i to z. So it would be that vector there. And that has to have a length of 3, which it does do because our circle has radius 3. Now for part B, we have to find the Cartesian equation of this circle. Obviously, we know the centre of the circle is 5, 3, and the radius is 3. So we could just straight away say that the Cartesian equation of the circle is x minus 5 squared plus y minus 3 squared equals the radius squared, which is 9. Another way of doing this would be to do it algebraically, and I think it's really important that you're able to do this algebraically, because some questions will require you to do it algebraically. So in order to solve this problem algebraically, we're going to say, well, z is going to be represented by a coordinate xy. So z is going to be x plus iy. And we know that z has to satisfy this condition, that z minus 5 minus 3i, the modulus of that, is equal to 3. So let's replace z with x plus iy. So basically what we're saying is we want to find all the coordinates x, y that satisfy this condition here. We're always going to do the same thing when we're doing it algebraically. We're going to collect together the real parts inside the modulus symbol. So we've got x minus 5 is the real part of this complex number. And we're going to collect together the imaginary parts. We're going to take I outside of a bracket. So we've got y minus 3i. So actually what this is saying is we're saying we've got this complex number with real part x minus 5 and imaginary part y minus 3. And the modulus of that complex number is equal to 3. Well, the modulus of a complex number is equivalent to working out the square root of the real part squared plus the imaginary part squared. If you don't like that, then think we've got this complex number here inside the modulus symbol, and we could think about that on the Argand diagram. I'm not sure where it is, but it doesn't matter. I'm just drawing the diagram to help us think about it. So this is our complex number that I've shaded in green. The real part is x minus 5, and the imaginary part is y minus 3. And we want the modulus of that green complex number, which is the length of the line from the origin to the point. So we're basically working out what's that length. And you can see that we can just use Pythagoras, which is what we've done here. So now we can square both sides of this equality, this equation, and we'd end up with x minus 5 squared plus y minus 3 all squared equals 9, which is what we got before. So this is the Cartesian equation of that circle. So in part C, we've got to work out what is the maximum value of argz. So remember, z lies on this circle somewhere, and we're basically saying where do we need to be on this circle in order to make the argument of that point as big as possible. So to help us think about this, I've got a little animation here. So this is the circle that z must lie on. So we know that when we move z around, it has to be somewhere on this circle, okay? And what we want to try and do is we want to try and find out where z needs to be to maximise the argument. Now remember, the argument is the angle that it makes with the positive real axis. So I've labelled that as this orange angle here. So we're just going to imagine moving around this circle, and you can see that the argument's going to get bigger. This argument here, this angle is increasing. And then it's going to get to a point on the circle where all of a sudden the argument starts decreasing. So you can see that the maximum argument possible, what makes that angle as big as possible, is when z is at a point where the line going from z to the origin is a tangent to the circle. Because you can see that when it gets past that point, the angle is going to decrease. And from this diagram, we can see it's roughly going to be 1.08 radians is going to be the maximum value of the argument. So our aim is to find the value of that angle there. Okay. So what we're going to do is we're going to use the fact that this line here, this dotted line, is a tangent to the circle. So if I draw in that tangent, the radius, to that point z, then we know that that's going to be a 90-degree angle. So we've just got to think about some circle theorems here. I've also noticed that the real axis is a tangent to the circle too. So I could draw a line down there, and that would be a tangent. Now there's a circle theorem that says if you've got an exterior point of a circle, and you've got two tangents going to the circle, if you draw a line from the exterior point to the centre of the circle, then it's going to bisect this angle theta that we're trying to find. So I'm just going to cross out theta for now and draw in that line to the centre of the circle. So actually we know that this angle here is half of the angle that we're trying to find. So that's theta over 2. And that angle there would also be theta over 2. Well, this helps us because we know that the radius of the circle is 3, so we know that length's 3, and we know that this length along the bottom is 5. And actually we can find out what this hypotenuse is here using Pythagoras. So that's root 34. And in fact, we don't actually need to find that because we could just use tan on this right angle triangle. So you can see that tan of theta over 2 is equal to opposite in this right angle triangle, which is 3, over the adjacent, which is 5. So we'll get that theta over 2 is equal to arctan of 3 over 5. So theta is equal to 2 lots of that. And we'll get that theta is equal to 1.08. And it's worth checking once you've found that angle that it makes sense. So we're saying that that angle there is 1.08 radians. And that makes sense because it's going to be past pi over 4, but not more than pi over 2. So it seems sensible.